what I want to tell today is a course which I also tell to my students, and that is the background of buckling. Yeah, and well, most of you have heard about we start with beam buckling because that is the easier one of the two, and they are linked to plate buckling, but we will see that later. In general, for beam buckling, we have two different directions. You have here simple beam buckling, so that the beam itself buckles. Within the beam, you also have torsional buckling. That's the second example, and the third one is, for example, if a single plate or single part fails, and then that can be a flexural-torsional buckling. So then one of these two flips to the side, and so it's not full torsion, but that is one part which fails. We also need to take into account that if we do an FEA model with buckling, it is important to include warping. And what is warping? That's two things. In general, if you have a beam element, the deflection is constant over the length. So if I wait, I'll draw that. If I have, for example, this beam with a load, then it deflects, and then the rotation is considered constant over the height. Yeah. What does it mean? And the deflection of your beam profile, in reality, that is related to the shear in your beam. And if I have, for example, an I-beam, then over the height, the shear deflection, the shear load is like this. That also means that the shear angle also scales in the same way. Sorry, it is like this. So in the middle, you have more shear than at the edge, and then you get deflections like this. And what does it mean? It means that this warping needs to be taken into account. For example, if I'm very close to a constraint, the stiff, if I apply a load here, then I have the torsional load, or if I apply a load here or a torsion over the actual axis, then I have on the top, I have a force in this direction here, and here at the bottom I could have something like this. And for open structures, the constraint here at the edge results into a tension and compression stress over the top plate, and that has a considerable increase in stiffness. That results in an increase in stiffness. And why is that important? I have here a picture with and without warping. In ANSYS you can put these things on and off, and you are using SimCenter now. For the Nastran solver, you can also there by default on or off. You cannot show the stresses, I think, over the beam, but with old ANSYS, with new ANSYS also not, but with old ANSYS you can do that. And here in this picture you see what the difference is. If you do not take into account this shear strength, so the stresses over the section itself, then you have standard beam theory, and you have a deflection which looks like this. So that is a constant rotation if I apply a constant torsion. You see here the deflection. So the rotation varies constantly over the length. And then the stress is, of course, only due to the synvenant stress due to torsion. But if we take into account the warping constraint, then you see first of all that the stiffness is 3 times higher. And if you look at the stresses, you see why. Because basically here at the top and at the bottom, you get a plate bending stress, because this plate wants to go into that direction and this one wants to go into that direction, and that the single plate, the single bending over the plate itself results in a much stiffer a much stiffer constraint. So if we do a beam buckling approach, so if we take a global model, this is something which you really need to take into account. I think you can see it from a simpler perspective. If I have symmetric closed sections like boxes or I-beams, they are open, but they are at least double symmetric. Then this warping is not that important. But if you have open sections, then this effect of clamping of this initial plates is crucial, and that results in a much higher stiffness and therefore also in a much higher buckling load than compared to a single beam. So in short, my conclusion, the conclusion for this is, if you use a beam model and you use a finite element buckling calculation, this warping is crucial. That needs to be included. The problem is that these things are hidden in the beam properties, so it's not so easy to figure it out. In our section, we're going to use limits based from the standard, so this warping effect is taken into account by default there. But if you want to compare this to a linear elastic buckling calculation, be aware that this warping needs to be it can be crucial. So if you really need an FEA linear buckling analysis, make a plate model if you have something like open structures, because the stiffness cannot be actually reproduced with a beam element. So this so far on beam buckling and some difficulties in there if you treat it with a finite element model. For now, we continue with the rest, which is where we use the theory of the simple beam theory and Euler buckling and how standards treat that. This is the standard theory. So we have a 1D beam element, we have a load here on the top, and depending if we have a small deflection here, you can come up with a buckling analysis which is of this shape, and where the N shape is the N is 1, that is this value. If I use N is 2, oh sorry, I get 2, N is 3, and so on. Yeah, so depending on the buckling shape, I get a different buckling risk. This is based on beam deflection, so there is not really something difficult, but basically what you get here is what we call the Euler buckling formula. And if you remove here the N value, because in general things buckle at the lowest buckling shape, then we go to the next page. The higher buckling shapes, by the way, are important if you do, for example, if you have impact loads or something. If you, for example, squeeze a can for beer or for Coca-Cola or something, you will see that you get a lot of higher order buckling values at the beginning if you slam it. So if you slowly squeeze your tin, you get one buckling load like this. If you do it faster, you can get the higher buckling modes as well. That's the same with beams, of course, and that has to do with the amount of mass. And a higher buckling factor, if it only buckles here, has a much lower mass component than if the full beam needs to deflect. Yeah, but if we do it slowly, in general, the lowest buckling mode is the one which is the most critical one. And if we look here, you will see this is what we call the critical Euler buckling load, and it has this shape. And instead of here, you see, so P square, L square, E and I, and this L square here, that's what we call the effective length. If we have, this is the default this is the default shape. So then this is the critical buckling length. So that's the Euler buckling length. But if we use different constraints, we can have a different value. And of course we can calculate it with the formulas and use the right boundary conditions. So here it's then clamped and there it's free. But it is much faster if we look at the shape of the buckling method. So what you see here, that this method here in reality, so the buckling shape looks, it is a symmetry plane here, so the real buckling shape is twice the length of the beam element. And in this way we can take this, if we modify the formula and take the length, the buckling length as it seems to be, then you will see that the buckling length, the buckling risk is 4 times lower because the length is 2 times the beam length instead of the standard one like this. Yeah. This is a very nice engineering concept, but there was somebody on, I think it was on Refi, and I'm not sure if it's still there, but there's somebody who thought, well, that it's nice to have these buckling values, but seeing is believing. I'll just make an example. So he made the standard beam buckling, where you can see here the loads. So this is pinned and pinned, so it can rotate here both at the bottom and at the top. And then he made different effects. If I use a fixed boundary condition and also fixed here, or pinned here and fixed there, or fixed and here free, you see that these shapes, this is a standard shape here, this one looks like this, so the real effective length is somewhere like this. And this one is pinned here and then somewhere around here, so let's say 0.7 times the real length. That is the buckling length as it seems, and this one is the same as the one where we started with, so the buckling length is twice this value. So here we have a list of what is the effect. Yeah, so fixed pinned is 0.7. Well, that is in fact the 1 divided by the square root of 2. So that is the real buckling length. So that is this one. But my message is you can quickly understand by visually looking at your beams, you can adjust the effective buckling lengths, and you can use these in the formula. By default, standards assume the standard situation, so with a buckling length of 1 times the beam. Take that into account, because that means that you can use this effect in for modification of the real buckling length in your model. For example, if I have a beam model where I have a connection here and a connection here, and then I don't know, this continues, something like that. If you want to take a simple modification, is for example, if the beam shapes are considerable, then you could say, okay, this is the buckling length in my beam model, but in reality it is supported here and there because these beams have a certain size, so that you can easily modify that buckling length to between these edges. Of course, taking into account that you need to figure out whether the beam section here really can transport the bending moment here at the beginning, so that you really have the effect of that it is supported here. Yeah. You also have standards which has standard modification factors to take into account these effects. But in general, the idea is, depending on the constraints, you can modify your buckling length, and you can still use the same formula. So it's a really simple, it is for beam buckling a quite simple formula, which is the basis for all the checks you do. Yeah, so you take into account the E, the A and the E, and you divide by the buckling length, and you do the times P square, so that is around 10. Okay. If we then go to a limit for a beam, we can say, okay, we have for axial load, we have basically, or the buckling effect. So this is this formula, where depending on the slenderness ratio, so that is the length divided by the ratio of duration. The ratio of duration, what is that? If I take the average area of a shape, that is the average distance to the neutral line for the whole area. Yeah, so, or if you take this formulation, if you assume, okay, we have a buckling limit. If that is a load, but we want to calculate with stress. So suppose that the fictitious stress when at Euler buckling, we assume it doesn't buckle, so we have an imaginary stress. So we have the buckling, the Euler buckling force divided by the area gives us the actual stress where you have when you can expect Euler buckling. If we take that into account in the original formula, then we get here, you can rewrite it like this, and then you see that the stress, the Euler buckling stress, so that is the stress equivalent to the Euler buckling load, has this formulation in here. So that is the slenderness ratio, that is E. So rho, that is E divided by A. So that is the moment of inertia divided by A, and then so then n the square root of that. And that is the radius of gyration. So the physical thing is what is the average distance to the neutral line? And so if I have if I have an imaginary beam with, let's take an I-beam, where we take the web as infinitely small, so then my radius of gyration is going to be from here to the center of the area. So it is a physical thing. Yeah, so that is good to take into account. If we take this radius of gyration and we divide that by the length of the buckling length, we get a slenderness ratio. And if we take this slenderness ratio here, then we see the buckling limit, which depends on the slenderness ratio. So the slenderness ratio takes into account the bending stiffness compared to the actual stiffness, and then you get this curve. So that is the Euler buckling curve. That is nice, because now then we can also say, okay, we can see that for high slenderness ratio, buckling is much more important than yield. If we take here 250 as a yield limit, so we have S235, then it's actually slightly lower. Yeah, but then we have two risks combined. We have here yielding of more material, and here we have buckling of the material. We also need to take into account, for example, the effect of offsets, because if you have a certain imperfection, so a standard deviation, you will see that the buckling load itself does not change, but the deflection increases a lot. Yeah, and the other thing what we see, if we have some kind of eccentric load, you will see, so here's the original buckling length, that if we have some of this eccentric load, so if we assume that if we do this in a simple formula and we ignore yielding, then this initial deflection does not have an impact. But if we take into account the yielding account, then at a certain point the corrective moment to keep the beam model of the beam stable reaches its limit. So if we have, for example, an offset depending on so here we take into account the different curves with a certain offset, where we have the initial deflection defined by the radius of gyration. So that is the effect is, okay, so how much bending moment do I have compared to my actual load? You will see that the original division, which is actually different two lines, will become some kind of a continuous curve, and you will see that this becomes much more smooth. How can you take this into account? Johnson made a modification to the Euler equation, and he took into account both the yield limit and the Euler buckling limit, and then he made what we now call the Euler-Johnson curve, which takes into account initially yield effect with a radius, and then it turns into it gradually changes, and then at around a limit of the slenderness ratio of around 100 for steel, exactly it's 89, then it turns into the buckling limit. So this is, if we take into account the effect of both the yield limit and the buckling limit altogether. How does this affect our checks? For my students, we use a simple approach. We have the yield limit, so that is this one. We say for up to a slenderness ratio of 10, so that the length divided by the ratio of duration is 10. The ratio of duration, if we take as a single block, is, let's say, a quarter to 30% of the width. So if this is the width, 30% of the width, that means that if we take 50%, so if we take all the edges, then the Euler buckling length of 10 means that the height is 5 times the base. Yeah. If that is the case, if you draw this, you will see, okay, in this situation, buckling limit is never a problem. This will always yield before it buckles. And if we take a slenderness of 100, then this thing is not 1 to 5, but then that's 1 to 50. So then we get something which is a lot higher, where this is, if this is 50, this is only 1, and then we can agree, okay, yeah, this probably will always buckle before it yields. That is the origin of the standard which we used in the Netherlands, and we also still use it in crane standard in the FEM, where we, instead of this Euler-Johnson curve, which is a bit more complex mathematically, they said, okay, let's take a simple line. We have yielding up to a slenderness of 10. With a slenderness of 100, we assume that we have always Euler buckling, and in between we draw a straight line. That's simple, no? And how does that compare to the Euler-Johnson criteria? You see that is not it is pretty good, but there is also something else which we need to take into account. If we just calculate the buckling risk or the yield risk, we also need to take into account the consequence, because for yield, if we go over the yield limit, my full section can become plastic, and it can, in general, the yield curve is not straight and then up to yield stress and then it's constrained. Then, oh sorry, where's where did I draw my formulas? Okay, I'll have to redraw it. If I have buckling stress, then so this is my deflection. This is the curve which you take into account for this Euler-Johnson buckling. Up to the yield limit, it behaves linear, and then we have the yield limit, and that's it. In reality, we have an increase in stress up till the ultimate stress. So we have in reality some extra reserve capacity. How do we take that into account? Here, if the yield stress is 235, then we take that with a safety factor of 1.5. 1.5, and that gives you an allowable stress of around 160, as you can see over here. This is 160. So here we take a safety factor of 1.5. While at the Euler buckling limit, the Euler buckling limit has a different characteristic, because if you have Euler buckling failure, then that's it. There is no increase in stiffness which saves you. It is when it collapsed, then you do not get an increase in stiffness. You even get a decrease, because with increasing load, you reach the yield limit and then it completely collapses. So to take into account that effect, you use here at the Euler buckling limit a higher safety factor of 2.5. Yeah. So the reason why this Euler buckling limit, the Euler-Johnson limit, is not used in the grain standard is twofold. One, it is a bit more complex, but also, how do we take into account the effect of the extra capacity of yield to ultimate compared to Euler buckling, which is immediately the maximum ultimate limit state load? So they did this by simple adding here the safety factor 1.5 up till the slenderness of 10, and here a safety factor of 2.5, and then using a straight line in between. So I have, the problem here is that I have a varying safety factor. So if I want to use a linear buckling analysis, I need to figure out, okay, using this curve and do reverse engineering of this formula, I need to figure out what is my required safety factor. This is also the case with Eurocode buckling, but then a bit more complex. But the idea is the same. If we compare then the limit of Euler buckling, of Euler-Johnson buckling, which is this original curve. So this is, if this is the yield stress, this is my Euler-Johnson curve, which goes smoothly from a transition from this point to that point. If we do that with a safety factor of 1.5, we get this blue curve here. If we do it with 2.5, we have this lower one. And if we then take the limit of this simple approach, you will see that with this straight line, it goes from this point to that point. Yeah, so again, if we assume that the Euler-Johnson curve is something we can get from the finite element model, you don't know whether something is okay if your safety factor or your buckling limit is between 1.5 and 2.5. You don't know whether that is okay or not. So that is an important remark if you want to use FEA buckling analysis, linear FEA buckling analysis. The effect of yielding is excluded, so you need to be aware of that. That is one thing, and the other thing is we have a variation in safety factor, which gives it hard to answer whether something is allowable or not. Okay, this one we skip. Let's go now to some models. So we figured out we have a formula. We have some kind of a limit. We take into account yielding and buckling together. Also Eurocode, basically all codes do that in some way or another. The AISC also has different the safety factor. This looks a bit like what the AISC has. Eurocode use modifications of the Euler-Johnson curve depending on the deviation from a perfect straight line. So it takes into account in the end what is the initial deflection of your beam, because that determines how your curve is, what the extra bending moment is. But if we look into a model, then we can see, okay, how do we treat this?